The strangest thing about sport is not how far bodies have been pushed, but how often the meaning of fairness changed. Ancient victory looked individual, yet the contest quietly depended on rules deciding which kinds of strength were allowed to matter. Those limits mattered because ancient Olympic sport was never a neutral measurement of humanity. Participation itself was socially restricted. The first revolution was therefore invisible. Sport became powerful when societies agreed that performance could be compared under shared constraints. Once performance could be compared, training stopped being merely preparation and became a technology for deliberately changing the athlete. That idea survives today. Equipment changes spectacularly, but every sporting era still engineers bodies around whatever its rules reward most. The stopwatch seems objective, but modern records emerged from something larger. Standardized distances, surfaces, timing, and equipment made comparison unprecedented. Industrial materials then changed the contest itself because shoes, tracks, and implements could return energy that earlier athletes simply lost. That created an uncomfortable question sports still cannot escape. When equipment improves performance, where exactly does the athlete end? Rules answered by drawing boundaries, yet every new technology forced governing bodies to decide which advantages still counted as sport. Paradoxically, tighter rules did not stop innovation. They redirected engineering toward the narrowest legal margins, where tiny gains become decisive. But technology did something even more profound than improve records. It made performances measurable at scales the human eye cannot resolve. Milliseconds became visible, and once hidden inefficiencies could be measured. Coaches began training movements that previous generations could only feel. The athlete was no longer competing only against rivals. Increasingly, each movement could be compared against a quantified version of itself. That measurement culture changed talent identification too, because exceptional performance could increasingly be separated into trainable components instead of mysterious gift. Yet better measurement exposed a deeper truth. Champions are not optimized for everything, but for extremely specific demands imposed by rules. Change the rules, and the ideal body changes with them, revealing that sporting excellence is partly an engineered relationship with constraints. This is why comparing champions across centuries is misleading. They were solving different physical problems under entirely different definitions of success. The next transformation moved inside the body, as physiology revealed that endurance depends less on willpower than on energy delivery. Oxygen became a performance currency because muscles can sustain far more work when aerobic metabolism keeps supplying usable energy efficiently. Training could enlarge that capacity, but biology still imposed ceilings through lungs, circulation, muscle chemistry, heat, and recovery. Sport, therefore, became a laboratory for a stubborn question. Which limits belong to training, and which belong to human anatomy itself? The answer became complicated when medicine learned not merely to repair athletes, but to restore performance with increasing precision. Recovery technology blurred another boundary, because returning an injured body toward normal function can also reveal methods for exceeding previous capacity. Then prosthetic engineering proved something extraordinary. Replacing a missing structure could create entirely new relationships between body, material, and motion. That did not erase biology. It revealed performance as a system where tissue, technique, and engineered materials exchange forces together. Exoskeletons push the same principle further transferring loads through external structures rather than asking muscles and joints to carry everything alone. Today's machines remain far from superhero suits, but they expose the mechanism future augmentation would need: power, control, and synchronization. Mechanical strength is actually the easier problem. The harder one is making a machine respond quickly enough to human intention. That delay matters because elite sport is decided in fractions of seconds, where sensing and reaction can matter as much as strength. Neural interfaces promise a different shortcut. Not stronger muscles, but faster communication between biological signals and external machines. But reading intention is not mind reading. Noisy biological signals must be interpreted statistically before they can reliably control anything. For sport, that uncertainty is crucial because an enhancement that occasionally misreads intent could turn speed into instability or injury. So the future of augmented competition depends less on spectacular hardware than on something less visible: trustworthy control at extreme speed. Once control becomes reliable, another constraint dominates immediately. Every powered advantage requires energy, and energy carries mass. That creates a trade-off biology already knows well. Carrying more stored energy can increase capability while simultaneously making movement more expensive. Heat follows energy, making cooling a performance problem whenever powerful electronics operate close to a working human body. Push powers still higher, and protection becomes inseparable from performance because faster collisions multiply the energy bodies and equipment must absorb. In ordinary sport, rules limit dangerous contact. Augmented sport would also need rules limiting how much kinetic energy technology can create. Fairness would become harder too, because competitors might arrive with fundamentally different combinations of biology, software, hardware, and financial access. Classification could therefore become as important as competition, because meaningful results require deciding which technological differences belong in the same category. Software introduces an even stranger variable, because two visually identical machines can perform differently simply because their control code differs. Competition might then resemble motorsport, where victory belongs neither to machine nor driver alone, but to the performance of their integration. The athlete of that future would be less a modified human than a coupled system whose weakest connection determines everything. And every connection creates failure points, from depleted batteries and overheated motors to sensor errors and mechanical fatigue invisible before competition. Reliability may become the new endurance, because finishing could depend as much on thermal margins and component life as cardiovascular fitness. Yet, removing biological limits would not remove strategy. It would simply replace familiar constraints with new ones engineers cannot ignore. Even gravity, the oldest sporting constraint, becomes negotiable once competition leaves Earth. But physics does not become optional with it. Without weight, muscles still generate force, but athletes cannot push against the ground unless something else supplies an equal reaction. That single law would redesign every orbital sport, turning walls, rails, tethers, and momentum into the equivalent of today's playing surface. Speed would feel radically different there, because momentum persists without the rolling resistance and repeated ground contact familiar to terrestrial athletes. But greater speed would make stopping the real event, because every joule of motion must eventually be absorbed somewhere safely. At that point, protective engineering would shape records just as strongly as muscles, because maximum performance becomes meaningless without survivable deceleration. The ultimate contest would therefore not be human versus machine, but competing philosophies about which limitations deserve to remain meaningful. Ancient athletes accepted limits they could barely measure. Future athletes may face the opposite problem, choosing which measurable limits to preserve. Sport began by asking what a human could do within shared rules, but augmentation changes the question itself. For most of history, the athlete's body appeared to provide a natural boundary. Muscles tired, bones tolerated only so much force, reaction times remained finite, and gravity demanded payment for every jump. Yet those boundaries were never entirely natural. Tracks became faster, shoes returned more energy, medicine restored damaged bodies, timing exposed invisible fractions, and training transformed physiology with increasing precision. Technology did not suddenly enter sport. It had been reshaping the meaning of performance all along. What changes with neural interfaces, powered limbs, and orbital competition is the scale of that intervention. Strength could depend on motors, reflexes on signal processing, endurance on batteries and cooling, while safety depends on materials capable of absorbing energies the unaided body was never designed to survive. Even in microgravity, physics refuses to disappear. Momentum, reaction forces, heat, and energy remain absolute constraints. So gravity-defying competition would not create athletes without limits. It would create athletes whose limits are increasingly chosen, engineered, and regulated. That makes the deepest future sporting question surprisingly ancient. Victory has never meant unlimited capability. It has meant excellence inside boundaries everyone agrees are meaningful. The technology may become extraordinary, but without trusted constraints, comparison loses its value. The future of sport, therefore, depends not on escaping every human limitation, but on deciding which limitations must survive for achievement to remain recognizable as sport.